Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. This is chapter 1, partial derivatives. We're in section 1.3, which is also partial derivatives. Today we're going to do partial derivatives of order 3 or higher and a quick introduction to partial differential equations. Let's get to it. All right, again, we're going to consider mostly focusing on functions of 2 variables or 3 variables. Sometimes when we have to go higher from when we need to, we'll have functions of 4 variables or higher, but for the most part, we're going to look at f of xy or f of xyz. So to start, again, when we define partial derivatives of xy, what do we have? We have essentially the 2 first order partial derivatives, and then in the second order we would have 4. We would have these 2 functions, and then we could take the partials with respect to x and y of this guy, the partial with respect to x and y of this guy. That gives us 4, but we found out by Clairaut's theorem that these 2 guys are in fact equal to each other, which is good. Once we take the second partial derivatives, these are all functions of x and y as well, so we can take their partial derivatives, and by Clairaut's theorem also we can notice that a lot of these guys will end up being equal for third order and fourth order, and then you can start counting how many distinct third order partial derivatives you have. Unless we really need it, first and second order partial derivatives will be enough for us. This is just like in one dimension. If we have a function of one variable, we're going to use the first and second derivative to sketch the curve of the graph of that function. Now what we're going to use in most cases, we can use the first order and second order partial derivatives to do most of the things we need to do the calculus for functions of more than one variable. Let's do an example. All right, example 1, consider this function of 2 variables, x squared y plus y sine x plus cos y. It wants us to find a bunch of partial derivatives of different orders. It wants the first partial derivatives, then it wants all the second order partial derivatives, then it wants a couple of third order partial derivatives. Let's compute. First of all, we need fx and fy. That's going to be fx is going to equal 2xy plus y cos x, and fy is going to equal x squared plus sine x minus cos y. Now to find the second order partials. To find the second order partials, we're going to do this. Fxx is the derivative of this one with respect to x. So that's going to give us 2y minus y sine x. Then we have fxy is going to equal, we can only compute one, but you can just to practice and verify that they're equal, compute both. Then we're going to compute with respect to y. That's going to give me 2x plus cos x. Then for the second order, starting with fy, we have fyx, the mixed partial, would be the exact same thing. We're going to get 2x plus cos x, and then fyy. Notice, of course, that's what Clairaut's theorem says, is these 2 guys are always equal to each other. And fyy is now the derivative of this with respect to y, which is going to give me negative sine y. This is wrong. This should be what? When we take the derivative with respect to y, it should have been negative sine y. I wrote it wrong. So this should be what? Negative cos y. Again, when we're taking the first derivative with respect to y, it should be x squared, then just sine x, and then negative sine y, not cos y. I wrote it down. I was going too fast. Now the third order ones. What do we want? For the third order derivatives, it wants fx x. So that's this guy taken with respect to x, and that's going to equal negative y goes x, and it also wanted fxy y, which is technically speaking this one, but either one will do. This one with respect to y, which is 0. Now we can talk about equations that have involved those functions and their partial derivatives. Let's do that. Okay, just like we had in chapter 0 of this series, we have many physical laws that also derive equations that have functions and their partial derivatives involved in them. These are going to be called partial differential equations. We're just going to give a quick snippet at the end of once we have partial derivatives. We're going to look at partial differential equations. In almost all scenarios of physics and science, when we derive these types of things from nature, there's 3 main forms. We have the heat or diffusion equation, we have the wave equation, and we have Laplace's equation. These are the 3 main forms of partial differential equations, and you should take a PDEs course if you are interested in that further. There's an entire course. Partial differential equations are extremely difficult, but let's just look at an example. Okay, example 2, solutions to the Laplace equation. The third form of a PDE essentially is this one called the Laplace equation, and classically solutions are called harmonic functions. And we want to know of these 2 functions, are they harmonic or not? They might both be, they might neither be, I don't know, one or the other. Let's check. 1. What do we have to show to ask if a function is harmonic? We need to know whether this is satisfied. So we're going to take the second partial derivative with respect to x and the second partial derivative with respect to y and see if those things, when we add them, we get 0. Doing that, ux is equal to 2x and uxx therefore is 2. Uy is equal to negative 2y, and uyy therefore is negative 2. And this says that uxx plus uyy is equal to 2 minus 2, which is equal to 0. So yes, harmonic. 2. This function now, we're going to have to take the second derivatives of these guys. When we do that, what are we going to get? First of all, ux is equal to what? Ux is the derivative of this with respect to x. So first of all, we have exponent on the inside could become number on the outside. So first of all, I can put this like 1/2. And then I'm going to take the derivative of this. This is going to give me, with respect to x, we have 1/2 1 over x squared plus y squared times 2x. So those will cancel, and I will get x over x squared plus y squared. Similarly, for uy, we're going to get 1/2 1 over x squared plus y squared times 2y, which will give me cancel y over x squared plus y squared. This is going to give me uxx is equal to x times x squared plus y squared minus 1. Derivative with respect to x. I know that's bad notation, but what do I get from this? I'm going to get x squared plus y squared to the minus 1 plus x times negative 1 times x squared plus y squared to the negative 2 times 2x, which is going to give me, now what am I going to do? When I clean this up, I'm going to take x squared plus y squared to the negative 2 out. That gives me x squared plus y squared, and then I have minus 2x squared. So that gives me, when I clean this up, y squared minus x squared over x squared plus y squared squared. Let's keep hold of that one. Let's move everything to the top and see what happens to this. Uyy is equal to, what are we going to get? Now we're going to take the derivative of this thing with respect to y. We are going to get, this is y squared plus x squared to the minus 1 with respect to y, which is going to be, we're going to get x squared plus y squared to the minus 1 plus y times negative 1 times x squared plus y squared to the negative 2 times 2y. This is going to give us what? We're going to get, again, we're going to pull out x squared plus y squared to the negative 2. This time I am left with x squared plus y squared, and then here minus 2y squared, which is going to give me x squared plus y squared to the negative 2 times x squared minus y squared, which is x squared minus y squared over x squared plus y squared. Therefore, uxx plus uyy is y squared minus x squared over x squared plus y squared plus x squared minus y squared over x squared plus y squared, which is now, the denominators are the same. We can add, cancel, 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 which is 0. Yes, harmonic. Next time we start tangent planes using another application of partial derivatives. We're going to look at tangent planes to surfaces of functions of two variables. Please subscribe right here and hit the notification bell. I'm Adrian, the Tutor Wizard. I'll see you next time.